Welcome to the next video in this series on chemical reactions and interactions. Previously, we had looked at reactions in videos linked in the description below regarding solids. Solids are a phase of nature that has a defined mass, a defined volume, and a defined shape. And when we looked at reactions involving solids, the defining feature was the mass, which had to be converted to the number of atoms or molecules in terms of moles by the molar mass. Liquids have more degrees of freedom and only have a defined mass and volume. They'll take the shape of the container. In the liquid phase in previous videos, we've seen aqueous reactions where the solute was dissolved in a solvent. In this case, the defining feature to convert to the number of moles was the concentration, the molarity, the number of moles of solute per liter of solution. Finally, now we'll look at the third common state of matter, gases. Gases are only defined by their mass. All of the variables on a gas are variable. Okay. However, they are definable. As one looks at the volume of the gas, one finds some very obvious things. As one blows up a balloon, it gets larger. This is Avogadro's law, which says the volume occupied by a gas is proportional to the mass or the number of moles of that gas. A second property of gas that everybody's familiar with is that if one has a balloon on the outside and then it suddenly gets cold, that balloon will deflate. This is an example quantified by Charles' law, which says that the volume is proportional to the temperature. The higher the temperature, the larger the balloon is. As the temperature decreases, the volume decreases. Thirdly, if you squeeze a balloon, that balloon will get smaller. In other words, you have Boyle's law, which says the volume is inversely proportional to the pressure. As one applies pressure, given an atmosphere's, the volume decreases. So you have a direct relationship with the number of moles, the direct relationship between volume and temperature, and an inverse relationship with pressure, or in other words, pressure times volume is directly related to moles times temperature. Relationship can be turned into an equality by adding a constant. In this case, the constant added to get the equality pressure times volume is equal to the number of moles times a constant, R, creatively called the gas constant, times temperature. The value of R and its meaning are actually very fundamental to understanding the physical universe. For starters, we'll just go with the fact that as a constant, R has a value of 0.0821 liters times atmosphere divided by moles per degree Kelvin, and that this is a universal constant, meaning every gas under any condition will follow the value of R. This in and of itself is an odd occurrence since all gases are different, and we'll see why this is so in the next video linked in the description below. For now, sticking with the basics, PV equals nRT is called the ideal gas law, where an ideal gas is defined as a substance where the volume is negligible. In other words, the gas molecules themselves take up no volume. Also, the interactions are elastic. The molecules will bounce off of each other and off of the wall with no attractions or repulsions. The use of the ideal gas law is again once best shown by using an example. In this case, the question is, what volume would 12.5 grams of nitrogen occupy at a temperature of 18 degrees C and a pressure of 810 millimeters of mercury? Reading the question for keys. The first key, that lowercase g, means that nitrogen is a gas. Anytime one sees the word gas, stated or implied, the answer always lies in the ideal gas law. PV equals nRT. Reading the question is asking for volume, which means that can be written to be equal to nRT over P, or N times 0.0821 liter atmosphere per mole degree Kelvin times T over P. Filling in the blanks with basics. First of all, I have 12.5 grams of nitrogen. Grams have to be converted to moles. 2 nitrogens weigh 28 grams. The grams cancel when one divides, so I have 0.446 moles of nitrogen. The value of R tells us also pressure has to be in atmospheres. On a barometer, there's 760 millimeters of mercury in 1 atmosphere. Dividing gives us 1.066 atmospheres. Finally, the units in R tells us temperature has to be in Kelvin, where the difference between Kelvin and Celsius is a constant 273.15. So 18 degrees C would be 291.15 degrees Kelvin. Plugging those in, 0.446 moles cancels, 291.5 Kelvin cancels, 1.066 atmospheres cancels. What doesn't cancel is liters, and since I am looking for volume, that would be the correct units. So after checking with the units, plugging in the numbers, one finds out that 12.5 grams of nitrogen would occupy slightly over 10 liters at 18 degrees C and 810 millimeters of pressure. These relationships can be expanded to looking at a reaction. For example, what volume of oxygen gas at 20 degrees C and 0.8 atmospheres of pressure is needed to react with 9 grams of methanol, CH3OH, to form CO2 and water? To summarize all of our relationships, before one proceeds in any question, one needs to know a balanced equation. Qualitatively, we have CH3OH and oxygen going to CO2 and water. Reading from left to right, I have 1 carbon on the left, 1 on the right for 1 CO2. I have a total of 4 hydrogens on the left, which means to get 4 hydrogens, I need 2 waters. And now, on the right, I have CO2 giving me 2 oxygens, and 2 waters giving me 2 more oxygens. So a total of 4 oxygens on the right means I would need 1.5 oxygens, O2 molecules on the left. To put a finishing touch on it, balanced equations are traditionally given in whole numbers. So a ratio of 1 to 1.5 to 1 to 2 would be 2 CH3OHs plus 3 oxygens goes to 2 CO2s and 4 waters. So to emphasize, one always needs a balanced equation. The second fundamental is I was given the number of grams of a reactant. One always converts grams to moles. CH3OH, 1 carbon, 4 hydrogens, 1 oxygen, weighs 32 grams. Dividing grams by grams per mole cancels out the grams and leaves me with 0.281 moles of my reactant. The third fundamental, once one has one's known, one goes to the balanced equation to find the unknown. In this case, I have 3 oxygens for every 2 CH3OHs, which means 0.281 moles of the methanol, CH3OH, would require 0.422 moles of oxygen to completely react. Finally, we're left with the fact that our reactant is now a gas and go back to PV equals nRT. So the volume would be equal to nRT over P. And in this case, I am looking for the volume of oxygen, which is going to be related to the moles of oxygen, 0.422, times the gas constant, times 20 degrees C, or 293 K, divided by 0.8 atmospheres, would mean I would need with moles canceling, Kelvin canceling, atmospheres canceling, the volume of oxygen needed would be 12.69 liters. So essentially, as with solids and liquids, the ideal gas law allows one to convert one's known data into moles. In the next video, which is shown in the description below, we will look deeper at the meaning of what the gas constant is, why it is a constant, and how that knowledge can help us have a better understanding of the universe around us and how to interpret the data that universe provides. Thank you for listening, and I hope you found this useful.